All right, everybody, good morning. I'm going to get started. As everybody knows, we have an exam next Monday. Are there any questions about the exam? We've got a lot of information about the exam on the website. There was a review session last night that I hope lots of you attended. There's another one on Saturday afternoon. And then just to remind you, I have office hours, kind of extended office hours today from 2 to 4. Any questions about what's going to be covered on the exam, what to expect? Okay. So we are in the middle of Chapter 6 right now, looking at acid-base concepts. And we ended last time discussing hard-soft acid-base, the Pearson acid-base approach. So this is a model, kind of a semi-quantitative model to understand trends in acidity and basicity, understand hopefully things like equilibrium constants for these sorts of reactions. And we broke the world down into whether an acid is hard or soft and whether a base is hard or soft. And we said that the hard are preferred and the soft are preferred. And at last time we ended here trying to understand a little bit, again, qualitatively about why hard and soft interactions lead to strong acid-base bonding, okay, strong or large equilibrium constants. And basically what it boils down to in this sort of picture is that when you have hard interactions, you have very low polarizability, and you're talking about kind of ionic interactions with these kinds of pairings. So you have good ionic-like interactions with hard, and this leads to strong interactions, okay, strong bonding. Soft is the opposite side, so you have highly polarizable entities here interacting, and you get more of a covalent kind of interaction, covalent kind of bonding. And so you have good covalent bonding when you have soft. You have good ionic bonding when you have hard, and in the mixed cases, not so good. So that's the general idea. And it has to do with orbital overlap and other concepts that we've talked about before. But again, keep in mind that this picture is a qualitative model. Okay? We're trying to categorize a very messy world, right, of acid-base chemistry into some sorts of concepts that we can use as rules of thumb to understand trends in reactivity. That's what we're trying to do here. One important thing to realize is that hard and soft is not the same as strong and weak acids and bases. So you can have a hard acid, let's say, that's also weak or strong. Okay? And so we have to consider both the strength of the acid and base as well as the hardness and softness of the acid and base in order to try to rationalize qualitatively reactivity trends that we see. So if we go back to that reaction that we looked at before, zinc oxide and N-butyl lithium giving us N-butyl zinc and lithium oxide. If you look just from a strength perspective, hard and strong acids and bases, you might consider that the equilibrium should not lie on the right-hand side of the equation, but should rather lie on the left. And one of the reasons you might think that is because zinc is a very strong, well, it's a strong Lewis acid, and oxide ion is a strong Lewis base. And so just considering strength, you would imagine that this is quite a stable compound, and we should actually lie on the left-hand side of the equilibrium. Okay? But like we described last time, when you also consider the hardness and the softness of the different entities that are involved in this reaction, you can understand that you have a strong driving force toward the products here because we have a hard acid and a hard base combined in lithium oxide. Whereas we have, with the zinc, we have sort of a borderline acid that goes from a hard base borderline acid to a soft base borderline acid. It's not a very strong driving force, perhaps. And the bigger driving force for the reaction in the hard-soft acid-base perspective is the lithium oxide formation. Okay? So we have to consider kind of both the hardness and the softness as well as the strength or the weakness of the acids and bases to get an idea about where these equilibria are going to lie. So again, it's a qualitative picture. Okay, so there's another approach that we can get a little bit more quantitative using the same sorts of ideas about covalent tendencies and ionic tendencies. And this is called Drago's, this is electrostatic covalent approach. Okay, so the EC approach, electrostatic contributions, covalent contributions. So this is a quantitative system where you have tabulated values that are generated from equilibrium constants and other experimental data, where we can estimate what the overall enthalpy change is going to be for a certain reaction. Okay? And in their model, okay, they consider an acid and a base, and they're looking at the enthalpy change of the adduct formation. Okay? The enthalpy in this Drago approach is given with this equation here, where we have the E of the acid and the E of the base plus the C of the acid and the C of the base. So what's E? E is the capacity for electrostatic or ionic interactions, okay, with the particular acid or base that we're talking about. And C is a measure of the capacity for covalent interactions. These are all given in units of energy per mole, okay, so kilocalorie or kilojoule per mole. Okay. And so the driving force for the reaction has something to do with the strength of the electrostatic interactions, the ionic, and the strength of the covalent interactions. And what's been generated is tabulated values of these 4 different parameters for lots of acids and bases. And so you can go to these tables and you can look them up, okay, look up these values, and then get a fairly nice estimate in many cases of what the enthalpy change is going to be. And it's actually surprisingly accurate for a lot of different examples. This is a scale that's potential energy scale, and so there has to be a reference compound because we're typically dealing with this sort of non-absolute energies that we need to worry about here. So what was chosen is iodine for the reference acid. Okay? And so this has Ca and Ea just equaling 1 kilocalorie per mole. And then there's 2 bases. There's this base here that's given an Eb value of 1.32, and there's diethyl sulfide, which is given a Cb value of something else, 7.4 in this case. Okay? And so what you have then is the ability to look up these values in tables. Okay? One of these tables exists in your book. And you can look at then the driving force for other acid-base reactions. For example, if we have iodine interacting with benzene, okay? This is a Lewis acid. This is going to act as the Lewis base, and we're going to form, in principle, an adduct here of the 2. And so we can go to table 6.17 in the book, which has some of these values. And we can look up what the different E and C parameters are. And for iodine here, of course, we have an E and a C parameter of 1 for both of those, okay, because this is turns out to be the reference compound that's used. And if we look up benzene, we see that we have an Eb value of 0.525 and a certain value for the Cb parameter. Okay. We can plug these into the Drago expression, and we can get out an enthalpy driving force here, which turns out to be negative 1.21 kilocalories per mole. And this is within about 10% of the experimental value. Okay. And in many cases, you can get values that are within 5% of experiment. Okay. And it's not perfect system, of course, so it does get into trouble, and it's not always accurate. But again, it's a good rule of thumb that's taken from experimental values, lots of equilibrium constants and other data, and kind of tried to distill the essentials of what's driving these acid-base reactions. Okay, and so there's, again, some truth buried in this kind of picture. It's not necessarily super clear exactly what's the essential truth that's in this model, but it has some experimental validity. Okay, so it works out in many cases. Here's an example of iodine, the absorption spectrum of iodine. You may know that iodine is this beautiful purple material. Right? It sublimes very easily, and so you can get a very nice purple flask full of iodine. This is the absorption spectrum here on this side for this adduct. When you have iodine interacting with benzene, of course, you're going to form a molecular orbital bonding and an anti-bonding molecular orbital when we form the adduct. And it changes the electronic structure of the iodine. And what you see in the spectrum is a small shift in the main peak. This is the iodine peak here. It shifts a little bit to the blue, just slightly. But more obviously, you get this new band that forms. So this is additional absorption within this adduct here. And this is the so-called charge transfer transition, where we have electrons being promoted from one part of the adduct to the other part of the adduct. Okay? So in this case, it might be from iodine to benzene, or it could be the other direction as well, okay, in principle. And so you get, you can use spectroscopy, of course, to determine some of the parameters associated with these different reactions. And one of the lessons here is that when you form an adduct, of course, we're changing the electronic structure of the molecule, of the acid and the base. Okay? And so we expect a different sort of absorption spectrum and other properties related to the electronic structure to change as well. Okay, so let's summarize this part before we start talking about acid-base strength. So we've talked about several models to describe acid-base chemistry, right? The Arrhenius model, the Lowry-Bronsted model, Lewis model, solvent system model, and others. We said that dative bonds, coordinate covalent bonds, are those that are formed when a ligand comes in and donates 2 electrons to a bond, right? Usually with a metal. And so we had an example with silver. We also have some kind of archetypal reactions that are Lewis acid-base reactions here. So we can draw this dative bond as an arrow. In many cases, that's not done, but you can do that. We can interpret the Lewis model in terms of MO theory. Okay? In order to make an adduct, we have the HOMO of the Lewis base interacting with the LUMO of the Lewis acid to form a bonding and antibonding orbital. Electron filling of the bonding orbital is one of the driving forces for the adduct formation. Okay? We introduced the idea of hard-soft acid-base models, okay, as a semi-quantitative way for understanding trends in acid-base chemistry. We have hard liking hard and soft liking soft, for some of the qualitative reasons that we discussed. And then finally, the Drago electrostatic covalent model, okay, provides a more quantitative method for understanding these same sorts of trends in reactivity. Okay, are there any questions about this section? Okay. Okay, so what we want to do today for the main part is to talk about acid-base strength. And so we know a lot about acid-base strength already from Gen Chem and probably from organic chemistry too. There's some mention of this. We know that we can interpret reactivity in terms of some different qualitative models or semi-quantitative models. These models are trying to use a conceptual framework, right, where we look at electrostatic and covalent character of the bonding to understand these trends. If we want to actually measure what the let's say enthalpy changes for these reactions, we have a number of different ways that we can do that we already know about. Right? Let's just remember what some of these ways are. So we can use calorimetry, for example, to directly measure the reaction enthalpy for an acid-base reaction. And this is a very standard way of looking at getting quantitative values for the delta H. We can also use Van Hoff's equation and look at the temperature dependence of the equilibrium constant. And from that, we can extract out the delta H parameter. And there's a whole host of other ways to do it. We can use various spectroscopic means, like the absorption spectroscopy that I showed. We can use that in principle to look at the equilibrium concentrations of the reactants and the products. So we can use infrared, we could use NMR, we could use UV vis, which is the absorption spectroscopy that I showed before. And this all allows us to get, all these kinds of methods allow us to get information about the overall delta H, delta G. So let's look first at how we can measure the enthalpy with calorimetry. Okay? If we have a reaction that goes to completion like this strong acid in water, right? Nitric acid, strong acid, we all remember that from the Lowry-Bronsted interpretation of acids and bases. If we have a reaction that goes to completion, we can directly measure the enthalpy change by using simple calorimetry. And from that, we have the heat change, right? The heat that's taken up or given off is going to give us the internal energy plus the work term, the PV term here. But the PV term, the change in volume, is essentially 0. And so this term drops away. And we have basically the heat that's measured is going to be related directly to the internal energy. And that's going to be basically equal to the enthalpy, okay, because the PV term in this case is so small. So we can measure just by looking at heat evolved or heat taken up, we can measure delta H. This is when we have a reaction that goes to completion. In many cases, acid-base cases, of course, the reaction does not go to completion. And so this cannot be used directly in this way because you've got a lot of undissociated acid, let's say, at equilibrium for many weak acids or for all weak acids. So if you have a reaction that does not go to equilibrium, like this one, okay, here we have acetic acid, which we know is a weak acid. So we're going to have an equilibrium here. We need to use another related procedure. And so this is where thermochemical cycles can come into play. So we can use Hess's law in this case. We can use reactions that do go to completion, combine them in some form to get the overall reaction that we're interested in. And that allows us then to estimate what delta H is. Okay? So how would we do this for this case? Well, we could take acetic acid and react it with a strong base. So this is a weak acid strong base reaction. That goes to completion. Right? We could measure that in a calorimeter if we wanted to. And then we can measure another reaction that goes to completion, strong acid, strong base. Okay? This is the reverse reaction for the autodissociation of water, okay? Giving us neutral water in this case. We can measure that if we wanted to. Of course, these values are already tabulated, so we can just look them up if we wanted to as well. We flip this reaction around, right? And then we add those two reactions together. And what we can see is that we're going to cancel out the OHs. We cancel out one of the waters. And we get then the overall reaction that we're interested in, this one, right? The weak acid equilibrium. And so using the using the Hess's approach, Hess's law approach, we can get the enthalpy change for the overall reaction that we care about from two enthalpies that we can measure more easily. In this case, we take reaction 1 and we subtract the enthalpy of reaction 2, and we get the overall delta H that we are looking for. So you can almost always play these sorts of games. This is accurate, of course, only to the degree that these values are accurate, right? So if you have junky values that go into your thermochemical cycle, then you're going to propagate the air in those values, and then the overall air in your total enthalpy change is going to be larger than you might hope. Okay? So you have to, of course, have good values to make this, this approach work out well. But this is a common way to do it. Okay? There's other complications in this approach, but in general, it works out pretty well. You have to be careful in what you're doing experimentally. Okay. Another way that we can do this is we can use Van Hoff's equation. So we can measure the KEQ at different temperatures. Okay? And then we can construct, plot that versus inverse temperature, get a line, and then fit it. Okay? If you remember what delta G is equal to delta H minus T delta S. And we can set the delta G equal to negative RT ln K for any reaction. And Van Hoff's equation is just a rearrangement of this delta G is equal to K expression. So we take this part, we rearrange so that we have an equation for ln of K. It's equal to the negative delta H over RT plus delta S over R. And you can see that this is a nice linear equation now. This is called Van Hoff's equation, if you remember. And so if we plot the natural log of the equilibrium constant versus 1 over T, we're going to get a straight line. And the slope is going to be related to negative delta H over R, and the intercept is delta S over R. Okay? And so this is how you can get delta H. So we plot natural log of Q, or natural log of K, versus 1 over, versus T over 1 over T, and we get a straight line. Okay? So let's do that for a simple example like this acetic acid example. So you can measure at different temperatures. Not a very wide temperature range is necessary. Different equilibrium constant values. We can plot those with the Van Hoff equation plot. So this is T to the minus 1, ln of K. And you get this fairly linear relationship. Fit a line to that, extract out the slope and the intercept for the line, and then we can determine what delta H is and what delta S is. Okay, so this is another way to do it. Okay, so this should be mostly familiar from Gen Chem, and perhaps from organic chemistry too. Okay, let me introduce another way to think about quantitating acid-base reactions here and getting delta H, and also getting kind of trends again. So we're looking at trends in reactivity. You can measure the proton affinity in the gas phase for different species. The proton affinity is a thermodynamic measurement. In the gas phase, you take, let's say, a base that's protonated, and you look at the energy that it takes to remove that proton to form the neutral base and proton. Okay? So we're just, in the gas phase, stripping a proton off of a molecule. It doesn't have to be a base, right? We could also do it for a neutral acid and form H plus and A minus. Okay? Either way, we call that the proton affinity. It's the affinity of this species for the proton that it's got. Okay? In order to do this, you can see that you're breaking a bond. Okay, so in all cases, the proton affinity is a positive value for delta H, because we've got to add energy in to break that bond. Okay? The nice thing about doing it this way, and the reason this has been done for thousands of different compounds, is because we avoid solvation effects in this case, because it's all in the gas phase. And so acid-base equilibrium constants have a lot to do with what the solvent is. Right? You get very different values for acidity depending on what the solvent is. Here we don't have any solvent. So this is sort of a pure, maybe the most pure method that we can use to measure trends in acidity. Okay? So we can consider this kind of be a pure view of the acid-base strength free of solvation effects. This is a table of these proton affinities from your book. And so what you see here is we've got a number of different simple compounds, okay? And we've got proton affinities from 1700 down to 1300 kilojoules per mole. Okay, so fairly large values. They're all positive, and of course this side is smaller than this side. Okay? So let's look at some of the trends here. These are labeled as the least acidic. These are labeled as the most acidic species. That's because the least acidic species, of course, takes a larger amount of energy to break that bond. The bond is weaker for the more acidic species, right? 1300, substantially different than 1700. Let's look at some trends that we might expect to see in these sorts of cases. Well, if you just look, period 1 isn't too interesting because it doesn't give you any trends. Period 2 is the first interesting one, and you can see as you go across the periodic table, from carbon to nitrogen to oxygen to fluorine, that we get weaker and weaker. Okay? And this is because of the electronegativity difference and the polar nature of the bond. Okay? As we have a larger electronegativity, as we move closer to fluorine, we pull electron density away from the proton and we make it more proton-like. Right? So there's a partial positive charge, increasing partial positive charge on the hydrogen as we move toward fluorine. That makes that bond weaker and easier to break. Okay? And so we see this sort of electronegativity-driven bond energy difference as we move across this series, this period, as well as this one, as well as this one. Right? So as we go from silicon to phosphorus to sulfur to chlorine, we see the same sort of trend. And we see the same sort of trend in period 4, right, from germanium over. Okay, so electronegativity mostly being the important factor here that's driving a difference in bond strength. So from left to right, we see this trend. What about from down an individual, down a column? Okay. So we can see the same sort of thing going on as we move down a column. So for example, down the halogens. We go from fluorine to chlorine to bromine to iodine. So what's happening here? The bond strength is also decreasing, and this is because we've got much larger halogens that are involved here. Right? So as we move down, the bond strength decreases because the halogen is much, much larger as we go from fluorine to iodine. And we can see a decrease in the delta H and an increase in the acidity. Okay? So HI is the most acidic in the gas phase. HF is the least acidic in the gas phase. So we see that for the halogens. What about for the group 6 elements? We see that for oxygen, sulfur, and selenium, the same idea. We see that for nitrogen, phosphorus, and arsenic, the same concept. And we see that for carbon, silicon, and germanium as well. Okay? As we go down a column, we see weaker and weaker bonding. And that leads to more acidity, greater acidity in the gas phase. Okay? Any questions about these basic trends? This is general chemistry, right? But it's nice how it plays out when you don't have any convoluting factors from solvents. It becomes quite clear. Okay? Very nice, consistent trends. Okay, so let's look now, using these proton affinities, let's look at some of the different different factors that influence basicity and acidity. And there's going to be 3 important things that we talk about. One is electronic effects, such as inductive effects. Second is steric effects. And then the third will be solvation effects. We'll bring things back into water or to other solvents. Okay? So first let's look at the effects of substituents on the molecule. So these are electronic effects. Okay? So we can use gas phase proton affinity measurements to examine how substituents change the overall acidity or basicity. In this case, we're going to look at the basicity, so whether something's a good or a weak base. Okay. What we have here is a trend where we go from ammonia and we just add methyl groups. We substitute the hydrogens with methyls. Okay. So we have 1 methyl group here, we have 2 here, we have 3 here. Okay. And I've ordered them in terms of the highest proton affinity being on this side and the lowest proton affinity being on that side. Okay. In other words, this one's going to be the best base because it has the largest proton affinity, the largest affinity for protons. Okay? And this one's going to be the weakest base. Okay? So highest proton affinity on the left, lowest proton affinity is on the right. How can we understand this trend as we add methyls, we get better and better base? Okay? Well, this is an example of an inductive effect, inductive electronic effect. Methyl is an electron donating type substituent. And so as we add more and more methyls to the central nitrogen, Okay? We have kind of electron releasing tendencies of these methyls, giving us more electron density on the nitrogen, making this nitrogen lone pair more basic. Okay? So essentially, bathing the nitrogen in more electron density, making that nitrogen then more prone to look for protons. Okay? So making it a better and better base as we make the electron density on nitrogen richer and richer. Okay? So this is a nice clean example of electronic effect and inductive effect. So one of the things to realize about inductive effects is that they can be fairly weak and they can be overridden by other sorts of effects in the molecules. So if we look, for example, at the effect of pi orbital interactions and pi effects, we can see something that doesn't follow the inductive trend that we would expect. Okay? This is an example, one of the cleanest examples, looking at the boron trihalides, okay? Boron, trifluoride, chloride, and bromide. We would expect just from an electron inductive perspective, electron withdrawing, that the fluorine, of course, is the most electronegative and is going to pull electron density away from the boron the most. And that should make the boron the most Lewis acidic. Okay? So it's going to be hunting for electron density. Right? So it should make the boron trifluoride the most Lewis acidic species. And because the electronegativity decreases in this direction, the tribromo compound should be the worst Lewis acid. Okay? But in fact, it's the reverse. And this is an example where we have an inductive effect driving a trend in one direction, but we have another effect coming in that overrides that trend. And this other effect are pi effects from this particular molecule. Okay, we remember that in boron trifluoride, we did the MO diagram. And you remember that the HOMO of the boron trifluoride is, or near the HOMO of the boron trifluoride, we have a pi bonding orbital. Right? There's a substantial amount of pi electron density on the boron. Okay? And it turns out that that amount of electron density, the interactions from the pi orbitals, gets weaker and weaker as the halogen becomes bigger and bigger. And so the amount of pi electron density around the boron is largest in the boron trifluoride. But as we go to the larger chloride and then the larger bromide, those pi interactions get weaker and weaker, and the electron density on the boron gets less and less. The pi electron density on the boron gets smaller and smaller. And so this is an opposite driving force for the just straight up inductive effects from the halogens. And this actually wins in this particular case. So the best pi bonding occurs here. Okay? That adds electron density to the boron and makes it less of a Lewis acid, or worse a Lewis acid. Okay? And the worst pi bonding is in the tribromo compound. And so we have the boron in that particular case the most hungry for electrons. Okay? And that gives us the best Lewis acid of this series of 3 compounds. Okay? So these particular trends here are shown for very simple, kind of clean compounds, where we're just adding methyls to the amine here, and we're just looking at a very simple Lewis acid and changing the halogen from one to another. Okay? Of course, when you have much more complicated molecules, the trade-offs, the competition between strict inductive factors, pi effects, steric effects, and other things can be quite complicated. Okay? So these are intended to show some sort of general trends. But again, when we look at more complicated molecules, it's not necessarily simple. And in many cases, it's impossible to say what's going to be more acidic than what, okay, without doing measurements. OK. So we have electronic effects that are one important part of acid-base reactivity. We also have steric effects. Okay? Steric effects come into play especially when we start talking about Lewis acid-base chemistry with large acids and bases interacting, okay, where steric effects can be important. Okay, so we can use, again, the gas phase proton affinities to look at how steric effects play out. Okay, we have this trend from the last slide, okay, where we know that the strongest base is here, and the weakest base is ammonia. Let's look at how sterics might influence this order of reactivity. Okay. This order is given for interacting with protons, right? That's the proton affinity order. But what if we change the Lewis acid from proton to something else? Okay. So let's look at the affinity for something that's a little bit larger, boron trifluoride. If that's the Lewis acid instead of proton, then you can imagine now we've got a slightly different situation because we need to worry about how the boron trifluoride can fit, right, into the spaces that are available around these different Lewis bases. Okay. So you can see right away what happens with the trend in reactivity. It changes. Okay. Again, the ammonia is the weakest base for interacting with boron trifluoride. But now the trimethylamine, right, is displaced from its highest position here to third. Okay? It goes from first to third. And then we have the single methyl and we have the dimethyl, okay, as being now the most basic in interacting with the boron trifluoride. Okay. So why is this? Well, we can understand this in terms of the amount of space that those different bases have around them to interact with the boron trifluoride. Okay. So the trimethyl is just too sterically hindered now to interact as strongly with boron trifluoride compared to those that have a few less methyls. So we have a balance between inductive effects and steric effects kicking in now. Let's look at the affinity for a couple of other Lewis acids. So here's the boron trimethyl, okay? And the order of reactivity is basically the same. Okay? So perhaps this molecule is not sufficiently big or significantly bigger than the boron trifluoride to really change the order. Okay? But if we go to something that's really quite large, like this tert-butyl, this tri-tert-butyl boron, this is a big, bulky Lewis acid now. And now again, we get a change in the order. Okay? The trimethyl is now the weakest base. Okay? We can understand that as probably mostly due to sterics. Okay? We just don't have enough space to interact with the big, bulky tert-butyl species. The dimethyl is third. Now ammonia itself gets kicked up into second place, but the best base here is the one that has one methyl group. Perhaps this is because it has a significant amount of room available to it, right? So sterically it's pretty good. And inductive effects are also present, right? So we have a little bit of inductive power from this methyl group being present. And so this might be the balance that between inductive and steric effects that allow this particular base to be the most reactive with this other Lewis acid, this bulky Lewis acid. Okay. So always we're going to have balances between electronic effects and steric effects in the gas phase even. And once we get into solution, then we also have interactions with solvation, right, that further complicate the picture. Any questions about the steric effects? Yeah, in the back.
So just by looking at like what we're given in the example, let's say instead of nitrogen and like ammonia, we have something else that's similar to it. Is there a way for us to predict like the affinity rather than just looking at the experimental data?
So you can predict trends in the affinity similar to what we've done here. So if you have, for example, like phosphine, like phosphorus version, so it would be a similar kind of approach, right? So if you had a very straightforward series where you're just changing the substituents of one of the reactive partners, like the base in this case, to be more and more electron donating or electron withdrawing, that would indicate probably that you're going to have a trend in the inductive effects that's going to drive the strength of the basicity. But if you have several different things changing at the same time, it gets complicated. And so it's not necessarily straightforward to figure out what the reactivity is going to look like. So these are trends that we're trying to identify. We're taking here kind of even overly simplistic trends, right, to show what effects are possible. And then how everything plays out is, in many cases, difficult to just identify unless you have a lot of practice like Professor Hayduk. So if you know a lot about molecular chemistry, then you can identify trends very easily. So he could probably tell you quantitatively, down to the third significant figure, what those different delta H values are.
You're really setting me up.
Yeah. Yeah. And yeah, he'll show you his magic starting next week. Other questions? Yeah.
So I don't understand why the NH3 is the lowest. I feel like NH3 is
Here?
the highest actual affinity.
The highest affinity in which case? In this simple case up here?
No, in the
Okay, so sterically it is the most accessible, right? So sterically NH3 should win, right? Because it's not got any bulky groups around it. But what we're saying is that it's always a balance, a competition between the different factors. In this case, the inductive factors and the steric factors. So NH3 might be the best on a steric perspective, but it's not the best on from an inductive perspective. And it's really the combination of those as well as possibly other factors that are important.
So in this case, inductive actually won, and then that's why NH3 is better.
Yeah, so you know, the nice thing about making these sorts of comparisons here with sterics is that you can change the sterics it's quite tunable. So you can compare with a number of different Lewis acids and see what the tipping point is for these different orders to change. Right? So we have the Lewis acid a little bit bigger, then a little bit bigger, then a little bit bigger. And we can kind of finely tune the reactivity of the base using this approach. Right? So that shows that you really have a competition between the inductive effects and the steric effects. And we can use the steric effects as kind of a very fine knob that we can tune, we can turn, and change the order of the bases. Yeah. Yeah. Any other questions? Okay. Okay. So a couple of additional interesting things that are related to acid-base chemistry that we need to bring up. One is that many metals are good acids. Okay? So metals themselves can act as acids. They are, of course, when we talk about coordination compounds, always acting as the Lewis acid. Okay? So we have Lewis acid-base adduct formation making metal complexes, coordination compounds. But more than that, okay, if we have certain kinds of metal ions, okay, in water especially, we can generate acidic solutions just from metal ions themselves. So let's look, for example, at the case of having chromium 3+ in water. Okay. If we add chromium 3+ in water, what we're going to get is an octahedral complex of waters around the chromiums. Okay. So this is the hexa-aqua complex. 3 positive charge on it, and because the chromium is fairly small and highly positively charged, the waters that are associated with chromium, the hydrogens on some of these waters are going to be acidic. Okay, so the protons on these waters can pop off, and we can get a hydroxide or a hydrido group that's generated on the chromium, and we can protonate water. Okay. And this gives us, in this particular case, chromium 3 in water gives us a quite low pKa, about 3.8 in this case. So when we have metal ions that are small and highly positively charged in water, what ends up happening is that we polarize, because we pull electron density away from this OH2, we polarize the OH group, and we generate a more acidic proton on those waters. Okay. And so we can expect to see with metals that are highly charged, let's say 3+ and higher, that they're going to tend to give us acidic solutions. So this is going to be true of chromium 3+, iron 3+, and other such species. So let's look at this a little bit more. This is the kind of thing that I was trying to describe. If we have a strong positive charge on the central metal, this is again a hexa-aqua complex here, we're going to pull electron density toward the metal, okay? And that's going to polarize the oxygen-hydrogen bonds. This is the hydrogen here in white and the oxygen here in red. So we're going to have a partial negative charge on the oxygen and a little bit more positive charge on the hydrogen. That's going to set those hydrogens up to pop off as protons. Okay. And so if you put iron 3+, for example, in solution, you get the hexa-aqua complex, and you'll have an equilibrium of the hexa-aqua with the penta-aqua hydrido complex where you've lost one of the hydrogens, one of the protons. And this is going to give you an acidic solution. Okay. So you can look up tables, of course, of pKa values for different metal ions in solution. So let's look at some of the trends that we see. So we've got iron, we've got chromium, aluminum, and scandium, and then a couple of others over here. Okay. These are the trivalent, and these are the divalent metals. If you look just, for example, at iron, when iron is 3+, it has a fairly low pKa. It's pretty acidic. When iron is 2+, it has a much higher pKa, right? About a factor of 1,000,000 higher in acidity constant. And this is because when you have iron 3, you've got a lot of pulling power from that central metal, okay, that's going to polarize that oxygen-hydrogen bond. If you have an iron 2, you don't have as much. okay, polarizing power. And so you're going to have a weaker acid with iron 2 than you would with iron 3. All of the metal 2, the divalent metals you can see, fall into a pretty narrow range of pKa values between about 8 and 10. And those that have trivalent species are consistently lower, okay? Between 3 and 5, let's say, something like this. Okay. So metal ion acidity is very important in any aqueous reaction chemistry. It's important in environmental chemistry, and it's also very useful in making and understanding metal complexes. Yeah, in the back.
So in the case of iron, is it the iron pulling the oxygen, or is it the oxygen pulling the iron? Because it showed that like oxygen is becoming more like partially negative, so is it the oxygen pulling?
So we can think of it like this. You have a very strong Lewis acid in the iron 3+, interacting with the Lewis base, which is the water coming in. The lone pair from the oxygen then is going to be the bond that forms between iron and oxygen, right? And the polarization of that, as well as everything else that's kind of near it, depends on the polarizing power of that central metal. So you pull that electron density from oxygen closer to the metal when you have a higher positive charge. And that also, by essentially inductive effects, pulls electron density away from the oxygen-hydrogen bond as well. So it doesn't just stop with that single bond, but it's an electrostatic effect, so it's felt throughout the entire molecule. So that's going to pull electron density out of, toward the oxygen from the hydrogen, toward the central metal from the oxygen. That's the idea. Other questions? Okay, let's talk about superacids and superbases. Actually, we'll talk mostly about superacids here. So this is a really cool part of acid-base chemistry that's discussed in some detail in your book. And so I just wanted to briefly mention it. We're not going to talk about it in great detail. But the idea is that you can generate something by using understanding of Lewis and Bronsted acid-base chemistry. Okay? You can generate acids that are more acidic than the benchmark here is pure sulfuric acid. Okay? Some of these acids, these superacids, are capable of protonating nearly anything, including things like hydrocarbons. And so some of the acids that have been generated and are classified as superacids can even dissolve wax, so they can dissolve candles by protonating the hydrocarbons. Okay? The acid that can do this was called magic acid, okay? In part because its ability to dissolve things that were thought to be undissolvable by acids. Okay? This is a table from your book showing some superacids and their relative acidities. The sulfuric acid benchmark is shown here. Pure sulfuric acid is what we're talking about. And this has an acidity, this is like kind of like a pKa value. Okay? This is called a Hammett constant of about -12. So anything that's got a more negative value than sulfuric acid is a stronger acid than sulfuric acid. And you can see that there's a number of acids here: perchloric, fluorosulfonic, this magic acid, and then the fluoroantimonic acid here that have substantially more negative H values, even as large as, say, 16 orders of magnitude different. Right? So this is a huge range of superacids. Okay? Let's look at how superacids are in general formed. Okay? You can make a superacid by reacting a strong Bronsted and a strong Lewis acid together. So let's focus on this one that's the most acidic down here, HF mixed with antimony, that's Sb, pentafluoride. Okay? So HF is a strong Bronsted acid when it's pure. Okay? You can see that the Hammett constant here is almost as large as it is for sulfuric. So HF is considered a strong Bronsted acid when it's not in water. Okay? And the strong Lewis acid is this antimony pentafluoride species. So what happens when you mix these? Well, one of the things that happens is that you generate a very, very, very reactive proton. Okay, this is not the only thing that happens, and this is a simplified picture of what's going on. But when you react HF with the pentafluoride, you can get a Lewis acid-base reaction. So with the Lewis acid here, pulling the fluorine in and generating antimony hexafluoride, okay, like this. And what that leaves behind is essentially a naked proton. And this is in, pure stuff here. This has got no water present. Right? So we have a very reactive, very unhappy proton there. And this is one of the reasons why this is the strongest superacid. Okay? So it's 10 to the 16 times more stronger than sulfuric acid. This is because it has this essentially naked or very loosely held proton, and that proton is going to jump onto almost anything it possibly can to become happier in its bonding. One of the reasons that we have a very, very strong acid in this case is because we have a very stable conjugate base of this now Bronsted kind of acid. Okay. So magic acids are used a lot in different sorts of inorganic and organic synthesis, stuff that my lab doesn't really do. Again, Alan's lab probably, no, you don't touch magic acids?
No.
So as you might guess, they are quite reactive and quite dangerous, I think, in lots of ways. But very interesting. And actually, the Nobel Prize in 1994 was awarded for this work, okay, for a chemist, to a chemist who's just up the road at USC. Okay, so let's finally, in the last few minutes, talk about solvation effects. Solvation effects have a massive impact on reactivity and can totally switch all the orders that we've talked about, right, in just the gas phase and energetics. And so we have the gas phase proton affinity for our 4 amines that we've talked about, okay, from ammonia to the trimethyl version. In the aqueous situation, the order changes. Okay? It doesn't change maybe that much, but it changes. We've got the trimethyl here as third, the single methyl is the second, and the strongest base now is the dimethyl. Okay? So why does this change just by putting it in water, right? So this is now not a proton affinity measurement anymore, but it's a pKb measurement or a pKa of the conjugate acid. Okay, this is the other way to look at this. So we're measuring pKa's, pKb's here, measuring proton affinities here. So why does the order switch? Well, it has to do with how these different protonated versions, or perhaps even the neutral bases, are interacting and being solvated by water. Okay? So this can have an enormous energetic influence on the stability of the reactants and the products and give us quite different reactivity. Okay? One of the main things to worry about in this kind of sequence is water's ability to solvate, and that has to do with the hydrogen bond. Okay? So in the case of the most reactive of the bases in this case, we have not just inductive effects, and in this case steric effects not being that important because we're talking about proton, but now we have the ability of water to deal with a protonated base, right, with the conjugate acid. And in this case, hydrogen bonding to this species is going to be better than, let's say, to this species because we have additional protons that are present on this species, right, that can interact with water, okay, and lead to a more stable product, better solvation, and this can drive the reactivity toward this sort of sequence, okay, from something that in the pure gas phase looked like that. Okay. So solvation effects are, again, very complicated. Okay, so you've got not just enthalpy, but you also have entropy that are important terms, and the entropy term can be kind of hairy to deal with and to predict what's going to happen. Let me finish by looking at the solvation effects in 2 different solvents to show really the massive impact that different solvation can have. Okay. What we have here is a number of acids, okay, neutral acids at the top and cations at the bottom. And we've got the pKa's in water and the pKa's in another solvent, dimethyl sulfoxide, DMSO. So water, of course, is a polar protic solvent. DMSO is this, okay? There's just 2 different ways to draw it, right? DMSO is polar and aprotic. So DMSO has, the same kind of polarity, order of magnitude polarity that water does, but it's not able to hydrogen bond as effectively. So the hydrogen bond network in water looks something like this, where you have 3 or 4 hydrogen bonds for each molecule, okay? The hydrogen bond network in DMSO is non-existent because it's aprotic. DMSO can accept the hydrogen bond from something that offers a hydrogen up, but it can't give any hydrogen bonds because it doesn't have any hydrogens to give. Okay? It doesn't have any hydrogen bonding possibilities. And so that has a profound influence on the ability to solvate different species, and in this case, on the acidity constants. In all of these cases here for these neutrals, okay, you can see that there's a huge difference in acidity between the water and the DMSO. And always in the water, the acidity is much better than it is in the DMSO. For example, HCl, negative 8 pKa in water, positive 2 pKa in DMSO. Why is that? Well, in this case, when we deprotonate any of these species, we generate an anion. And it has to do with the stability of the anion in these two different solvents. And water can hydrogen bond to the anion and can stabilize it. But DMSO cannot hydrogen bond to the anion. And so it can't stabilize it nearly as well. And so that's one of the major, perhaps the major driving force for the difference between the acidity in water and DMSO. Okay? So that explains sort of the neutrals. If you look at the bottom, though, you see an interesting change. For the protonated acids here, right, these amines, right, these nitrogen-based acids, we see that, first of all, the difference is much smaller now, okay, in acidity. And actually, the water is weaker than now the DMSO. Okay? Not by that much, but it's weaker. The reason that these are much closer in value to each other now is because when you deprotonate these species, you generate what? A neutral species. And it's not nearly as important to hydrogen bond to stabilize the neutral as it is for the anionic version of the conjugate bases for these acids. And so the stability and the reactivity of the acids for the cationic acids, much more similar in the two solvents. So again, driven by the absence of a hydrogen bonding capability in DMSO. So that's these two down here. And then let me just say a few last things. You can see if you look at water and methanol, in water it's very, very similar. In DMSO, it's quite different. Okay, so this shows you again just solvation being very important. And finally, the acidity of water itself, in water, much, much higher than it is in DMSO by about 16 orders of magnitude in the equilibrium constant. Right, so truly massive impact of the solvation on the reactivity and the energetics of these reactions. Okay, then we'll end here. We'll talk about leveling effects on Wednesday and then start with chapter 9, I think, starting on Wednesday. See you at the exam on Monday. Thanks.